Welcome to today's paper reading. Today's paper is titled, SimPO, Simple Preference Optimization with a Reference-Free Reward. This paper was published as a preprint by Meng and colleagues from the University of Virginia and Princeton University. The SimPO model with layer normalization, LN, consistently achieves a positive reward margin for all response pairs, regardless of their length difference, and consistently improves the margin over the SFT model. In contrast, SimPO without LN results in a negative reward difference for preference pairs when the winning response is shorter than the losing response, indicating poor learning for these instances. The target reward margin gamma in SimPO affects the reward accuracy on a held-out set and win rate on alpaca eval 2. Increasing gamma tends to improve reward accuracy but can also lead to a trade-off in generation quality. Table 1 presents the length-controlled win rate, LC, and raw win rate, WR, of top models on the alpaca eval 2 leaderboard, along with their generation lengths. The models we trained are highlighted in bold. This table provides a comparative view of the performance metrics of various models, emphasizing the effectiveness of our trained models in terms of both win rates and response lengths. Figure 1 illustrates the key difference between SimPO and DPO in their reward formulations. SimPO employs the average log probability of a sequence as its implicit reward, which aligns better with model generation metrics. In contrast, DPO uses the log ratio of the likelihood of a response between the current policy model and a supervised fine-tuned model. This figure highlights that SimPO consistently outperforms DPO across various benchmarks, including alpaca eval 2 and ArenaHard. Table 2 provides a detailed overview of the evaluation benchmarks used for assessing model performance in conversational abilities. It includes specifics on the number of examples, the baseline models, the judge models, the scoring types, and the metrics used for each benchmark. For instance, alpaca eval 2 uses 805 examples with GPT-4 Turbo as the baseline and judge model, employing a pairwise comparison scoring type to determine the win rate. Similarly, ArenaHard uses 500 examples with GPT-4-0314 as the baseline and GPT-4 Turbo as the judge model, also using a pairwise comparison for scoring. MTBench, on the other hand, covers 80 examples without a specified baseline, using GPT-4 and GPT-4 Turbo for single-answer grading to produce an average score. This table is crucial for understanding the methodologies behind the evaluation of models in these benchmarks. Table 3 presents various preference optimization objectives used in the study. The preference data is structured as X, YW, YL, where X represents the input, YW is the winning response, and YL is the losing response. The table lists several methods including RLHF, SLCHF, IPO, CPO, KTO, ORPO, and RDPO, each with their specific objectives. The study compares SimPO with these methods to highlight its performance in preference optimization tasks. Table 4 presents the results of various methods on the alpaca eval 2, ArenaHard, and MTBench benchmarks under different settings. The metrics used for evaluation are length-controlled, LC, and raw win rate, WR. The SFT models for base settings are trained on the UltraChat dataset, while off-the-shelf models are used for instruct settings. The table highlights that SimPO consistently outperforms other preference optimization methods across all benchmarks and settings, demonstrating its robustness and effectiveness. Table 5 presents the results of ablation studies conducted under the Mistral base and Mistral instruct settings. The study focuses on the impact of two key design elements of SimPO, the removal of length normalization in EQ 4, and the setting of the target reward margin gamma to 0 in EQ 6. The findings indicate that removing length normalization has a significant negative effect on performance, leading to longer and repetitive outputs. Additionally, setting the target reward margin to 0 also results in performance degradation, suggesting that it is not the optimal configuration. These results underscore the importance of both design elements in maintaining the effectiveness and robustness of SimPO. Figure 2 illustrates the impact of length normalization, LN, on response generation. Panel A shows the relationship between the reward margin and the length difference between winning and losing responses. Panel B presents the Spearman correlation between the average log probability and response length for SimPO, highlighting the effect of ln. Panel C contrasts this with the Spearman correlation for SimPO without ln, demonstrating the difference in response length characteristics when normalization is not applied. Figure 3 presents a study of the margin gamma, focusing on three key aspects. Panel A shows the reward accuracy and alpaca eval 2 LC win rate under various gamma values, providing insights into the model's performance with different reward margins. Panel B illustrates the distribution of reward differences under different gamma values, highlighting how the margin affects the spread and concentration of reward differences. Finally, Panel C displays the log likelihood distribution on chosen responses under different gamma values, indicating how the margin influences the likelihood of selected responses. Figure 4 presents a detailed comparison between SimPO and DPO, focusing on three key metrics measured on ultrafeedback. Part A illustrates the Spearman correlation between the average log probability and response length for DPO, highlighting its relationship with sequence generation. Part B shows a contingency table of rankings based on DPO rewards and the average log likelihood, providing insights into the reward distribution during training. Lastly, Part C contrasts the reward accuracy of DPO and SimPO, indicating which method more accurately assigns rewards based on response quality. Table 6 presents the Spearman correlation coefficients, ρ, between the average log likelihood of responses generated by different models and their respective lengths on a held-out dataset. The correlation for SimPO without length normalization, SimPO without ln, is 0.34, indicating a moderate relationship. DPO shows a stronger correlation of 0.82, suggesting a high positive relationship between log likelihood and response length. SimPO, with its correlation of 0.59, demonstrates an intermediate relationship, indicating a balance between the two extremes. Figure 5 provides a detailed comparison between SimPO and DPO models. Part A illustrates the KL divergence from the policy model to the reference model on winning responses under different beta values in both DPO and SimPO. Part B shows the alpaca eval 2 LC win rate for DPO and SimPO with varying beta, highlighting their performance differences. Lastly, Part C presents the runtime and memory usage metrics for both models, offering insights into their efficiency. The primary objective of this research is to align large language models to a process called joint preference optimization. This approach is detailed in the AR14 preprint AR14, 2404.00530, published in 2024. Additionally, the research draws on the Open LLM Leaderboard, a resource created by Edward Beeching and colleagues, which is available on the Hugging Face platform and was published in 2023. The historical context provided by seminal work from Bozer, Guyan, and Vapnik is also considered, highlighting its relevance to the current research direction. The importance of hyperparameter tuning in preference optimization methods cannot be overstated. It is crucial for achieving optimal performance, yet this aspect may have been underestimated in prior research, potentially leading to suboptimal baseline results. To ensure a fair comparison, we conduct thorough hyperparameter tuning for all methods compared in our experiments. For the general training setup, we use a learning rate of 2 times 10 to the power of -5, a batch size of 128, and a maximum sequence length of 2048. These settings are applied to the base training setups using the UltraChat 200K dataset. Additionally, we use a cosine learning rate schedule with 10% warm-up steps for one epoch, and all models are trained with an Atom optimizer. Method-specific training hyperparameters vary significantly and greatly influence benchmark performance. Therefore, we individually search the learning rates in the range of 3 times 10 to the power of -7, 5 times 10 to the power of -7, 6 times 10 to the power of -7, 1 times 10 to the power of -6 for each method. Detailed information on method-specific hyperparameter search ranges for baselines can be found in Table 7. Table 8 shows the specific hyperparameters used for SimPO under each training setting. Table 7 outlines various preference optimization objectives and their corresponding hyperparameter search ranges. The RLHF method aims to maximize a combination of log probabilities of winning and losing responses, penalized by a hyperparameter lambda. The DPO method uses a sigmoid function to balance the log probabilities of responses from the model and a reference model, controlled by a hyperparameter beta. The SimPO method introduces an additional term gamma to adjust the balance between the log probabilities of different response lengths, with hyperparameters beta and gamma tuned within specified ranges. Table 8 details the hyperparameter values used in the SimPO method across different training settings. The settings include Mistral base, Mistral instruct, Llama 3 base, and Llama 3 instruct. Key hyperparameters such as beta and gamma vary across these settings, with beta values ranging from 2.0 to 2.5 and gamma values from 1.6 to 0.3. Additionally, the learning rate is specified for each setting, ranging from 3 times 10 to the power of -7 to 1 times 10 to the power of -6. These hyperparameters are crucial for the performance of the SimPO method in preference optimization tasks. In this section, the authors detail the experimental setup and results. They utilized the atom optimizer for all experiments and performed a grid search on the temperature hyperparameter for the Llama 3 base setting with DPO. The experiments were conducted on a powerful computation environment consisting of 8 times H100 GPUs. For downstream task evaluation, models were assessed on the Hugging Face open leaderboard across various tasks such as Mengzhou, ARC, and HeliSwag. The authors observed that the effect of preference optimization varied across tasks. They found that knowledge was largely retained with minimal loss, reading comprehension and common sense reasoning improved, and there was a consistent improvement in truthfulness. However, math performance on GSM-8K showed drops for most methods except ORPO, which retained performance due to its supervised fine-tuning loss. Figure 6 presents 2 key analyses: A likelihood length correlation plot for the Mistral SFT model fine-tuned on UltraChat 200K, and B, a contingency table ranking based on SimPO rewards and the average log likelihood, both measured on the training set. These visualizations help in understanding the relationship between response likelihood and length, as well as the performance metrics derived from SimPO rewards and log likelihood. Table 9 presents the evaluation results of various downstream tasks from the Hugging Face open leaderboard. The tasks include MLU, ARC, HeliSwag, Truthful QA, Winograd, and GSM-8K. The results indicate that while preference optimization methods generally maintain or slightly improve performance on tasks like MLU, ARC, and HeliSwag, they consistently enhance performance on Truthful QA. However, there is a noticeable drop in performance on GSM-8K, particularly for methods other than ORPO. This table highlights the varied impact of preference optimization on different types of tasks and underscores the need for a comprehensive analysis to understand these effects better. Figure 7 presents the win rate heat map for Mistral base and Mistral instruct models on the Alpaca Eval2 benchmark. The heat map visually compares the win rates of these models against the baseline model, GPT-4 Preview 1106. This visualization helps in understanding the performance differences and relative strengths of Mistral base and Mistral instruct in various evaluation scenarios. Figure 8 presents a heat map illustrating the win rates of Mistral base and Mistral instruct models on the ArenaHard evaluation dataset. The heat map visually contrasts the performance of these models against the baseline model, GPT-4-0314. This comparison highlights the relative strengths and weaknesses of each model in a challenging evaluation context, providing insights into their performance characteristics. Figure 9 presents an example of a response generated by the Mistral base model trained with DPO. The input question is about determining if a person is genuinely interested in a conversation or just being polite. The DPO model's response lists several general signs, such as active listening, follow-up questions, and body language, to indicate genuine interest. This structured approach helps in understanding the relationships between different points, making the answer more readable and easier to comprehend. Table 10 presents detailed results from the Alpaca Eval2 and ArenaHard benchmarks. It includes length-controlled win rates, LC, raw win rates, WR, and standard deviations, STD, for various models. Additionally, it provides the average generation length for Alpaca Eval 2 and the win rate with 95% confidence intervals for ArenaHard. This data helps in understanding the performance and variability of different models across these benchmarks. Table 11 presents the average response lengths for models trained with Mistral Base or Mistral Instruct on Alpaca Eval 2 and ArenaHard. Key data points include Mistral Base achieving a length-controlled win rate, LC, of 21.5% with an average length of 1868, and Mistral Instruct with an LC of 32.1% and an average length of 2193. Additionally, the SimPO model without layer normalization, without LN, shows an LC of 11.9% and an average length of 2345. Figure 10 presents an Alpaca Eval 2 generation from the Mistral Base model post-training with SimPO. This figure serves to contrast the output generated by the DPO model, as illustrated in Figure 9. The key focus is on how the SimPO training influences the structure and readability of the model's responses, aiming to provide a more organized and detailed answer compared to the DPO model's bullet point style response. Figure 11 presents a comparison of Llama 3 Instruct, Llama 3 Base, and GPT-4-1106 preview models in answering the question about the language spoken in Argentina. Llama 3 Instruct, trained with SimPO, delivers a well-formatted and detailed response, focusing on rioplatent Spanish and its unique characteristics. In contrast, Llama 3 Base, also trained with SimPO, provides a concise answer mentioning Argentine Spanish. GPT-4-1106 preview, while including details about rioplatent Spanish, lacks the structured format of Llama 3 Instruct, making it harder to parse. This case study highlights the superiority of the instruction-tuned model in providing comprehensive and readable answers. In this section, we discuss the updates to the Llama 3 Instruct setting, focusing on the utilization of a stronger reward model. By switching from PARM to ARMO-RM, we observed significant improvements in model performance. Specifically, SimPO achieved a 53.7% win rate on Alpaca Eval 2, which is a notable enhancement. We also adjusted the hyperparameters, setting beta to 10 and gamma to 3, while maintaining other parameters consistent with the original Llama 3-8B Instruct setting. Additionally, with a robust SFT model and improved data quality, the differences between various algorithms, such as DPO, become less significant, highlighting the importance of high-quality data and preference optimization. Table 12 presents the results of the Llama 3 Instruct 8B setting, which uses preference labels annotated by a stronger reward model, ARMO-RM version 0.2. The table highlights that SimPO version 0.2 achieves a 53.7% LC win rate on Alpaca Eval 2, surpassing the previous version by 9.0 points. Additionally, SimPO version 0.2 maintains an advantage in producing shorter sequences, resulting in a significantly better LC win rate on Alpaca Eval 2. These results underscore the importance of a high-quality preference optimization dataset for enhancing model performance. Table 13 presents the evaluation results of various downstream tasks on the Hugging Face Open Leaderboard. The tasks include MLU, ARC, HeliSwag, Truthful QA, Winograd, and GSM8K. The table compares the performance of different methods such as SFT, RLHF, SLCHF, DPO, IPO, CPO, KTO, ORPO, RDPO, and SimPO. Additionally, it highlights the performance of Llama 3 Instruct version 0.2 across these tasks, providing a comprehensive view of its effectiveness in various scenarios. In this study, the performance of SimPO was found to have a similar raw win rate when compared to DPO, IPO, and RDPO. Specifically, DPO also exhibited a comparable raw win rate, as did IPO and RDPO. These findings suggest that all four methods perform similarly in terms of raw win rates, indicating a level of parity in their effectiveness. Thank you for watching.